in this part of this talk, it's again kind of moving back to the technology, and I hope this would be additional food for thought for follow-up discussions that we're going to have at the end of the tutorial. And this part is a little bit re-emphasizing the applicability of named data networking for IoT environment. And before I start, this is effectively a highlight of how we do things in TCP/IP infrastructure today, or how IoT inherited the elements of TCP/IP infrastructure. So there's a lot of point-to-point connectivity that we actually not just connectivity, but rather connections that the IoT applications are forced to use. So for example, and in addition to cloud dependency, that kind of a semi-result of this dependency on point-to-point connections. So for example, I have a Nest at home, I have a phone, but to communicate between my phone and this Nest controller, actually going through the cloud. I have kind of a faith in the Google that it's not going to destroy my home, even like I'm right now in Baltimore, but who knows? Look, maybe somebody hacks the Google, and it's my temperature in my home will be set to whatever 50 degrees, and I don't know what's going to happen. And another part that is kind of crucial for NDN perspective is even though we have the concept of IoT, Internet of Things, we're not really talking about things or maybe matter, but rather talking about the specific controllers. So every time we do something, it's about the controller that measures, but maybe measures temperature, or controller that controls the temperature. And kind of in all applications have to frame the conversation within parameters, instead of talking about the things themselves, like a temperature or like the wall, pH of the water in the ground. And to give you additional highlight of kind of this inconsistency or incongruency between the applications, what the application wants and what the network provides, is this, in quotes, simple stack of IoT applications that they have to have. So kind of we have a link layer connectivity technologies. On top of we have to run some form of IPv6, like a 6LoWPAN. Then we do TCP, UDP. Then we do hopefully some form of security of point-to-point connections, either HTTP, QoP, and have to use DNS to tie everything together. We have to use DHCP to give us all IP addresses. And only then IoT applications maybe be able to actually do the job. Versus, okay, I skipped the picture of what versus in NDN the picture becomes. So in NDN, everything becomes the name. So like if something wants to operate, to get the picture from somewhere, there is a name for that. So you want to do something, there is a name for that. And in addition to that, just having the names, there is also alignment between kind of what network provides and what application wants. So now you actually can talk about the temperature. So if I want to get the temperature in this room, and I know the convention of some temperature application, I just send interest with the context of this room, asking the temperature, and that interest may be answered by anybody in this room. Or like in aircraft example, if I want to get some sightings from specific angle, anybody from that position can get me that sightings. So that's pretty good. I don't really need to care about, oh, I need that specific aircraft. Of course, this requires quite a bit of security, so because you don't want to rely on some random person to give you that data, and that's the benefit of NDN, because that data is being by itself secured. And I'll try to give some hints of how we operate in this context. And Lisha already emphasized that there is a request-response semantics brings a lot of benefit for delayed, I would say, ad hoc and broadcast style communication, intermittent connectivity, because you're no longer required to have a producer and consumer to exist in the same time. And this is exactly what Tamer was highlighting in the experimentation scenarios. Like you send a request, the guy may not be like you potentially in that scenario you never have point-to-point connectivity between like a consumer and producer at the same time, or for at least for as long period of time to get this large files. So that's why IP connectivity completely failed, because you just cannot do this. And to kind of highlight of power of the names, I just tried to give you example of different things what name can represent or name data can represent, which kind of overlaps with what we talked before and the small conversations that we had in the room. So this data, the name of this data can be actual data, or like a piece of frame, video frame, or some positional data. It can be command to projectors. If I want to send some command to project my slide on a projector, I can have something like that. It can be a function. So this is another area that unfortunately we don't have time to talk about. But NDN also nicely ties together processing within this networking environment, because everything can be named. Like you can have, and hierarchical names gives pretty quite flexibility of what you can do. Like what in names. And some additional information, but the last thing I want to emphasize here is cryptographic keys, because everything is data, everything can be named, and the cryptographic keys, either for encryption or authentication, can also be that pieces of data that can float inside the network or can be provisioned, but you always can get them by this name. And let's see, of course, they have to exist in the first place. This is a small repetition of what Alicia already highlighted. In NDN, the bootstrapping process is happening at the application level. And there is a name discovery, but this is a different story. But the bootstrap process itself is to know some naming conventions, how this application operates, how the positional data is structured in the first place, is built into the application itself. The piece that is not built at the application development, but rather during the deployment process, is the security. So you have to add, when you deploy the application on aircraft, when you deploy the application on Humvees, those have to receive proper credentials, like in order to meaningfully produce data or have a meaningful way to get access to protected data. So we have a few solutions kind of currently in works. Unfortunately, I didn't have time to talk about them, but some of them are still in development stage, of course. And so this is kind of to highlight this, even though I mentioned the word bootstrapping, and here in some cases there is no bootstrapping necessary. You don't need to have IP addresses. You just got this NDN box through into the field, and it can now operate, assuming it has already provisioned with proper credentials. Now I want to switch gears a little bit of kind of a little bit details on how NDN operates for authenticity, for data authenticity. Lisha, in the first part of the presentation, emphasized that each data packet that is being transferred is not just named, but rather has this unique signature that associated with the data packet, and the signature can be used to authenticate validity of this data packet. But it's actually, I mean, the benefit of this data is effectively secured or can be retrieved from anywhere and kind of stays, have this property of authentication, no matter whether it's in moving around, like being transferred right now, or stored somewhere, or like being retrieved at some point later. But again, this is just was half of the story. The additional key half of the story is that it's not just signatures present in that data packet, but rather name of the key that needs to be used to authenticate this data packet is also part of the data packet itself. And why do we need this? So you can just use that name to fetch that data packet that corresponds to the key. And that data packet also has a signature because it's an NDN data packet. It also has a name to authenticate that data packet, so it can, and so you can fetch that one. So effectively, it creates some chain of certificates. Yeah.
If you consider the scenario that was presented before, So basically, we have this aircraft, which is the gateway for most of things. So imagine I have my key, so it's not UCLA, but it's my house.
Yeah.
Everything was going through this gateway, aircraft gateway. If the aircraft gateway was forging signatures, it was also the one you had to go to fetch the wireless key.
Yeah.
So
the trust is not just about the set of or sequence of signatures. There is always the anchor. So you cannot simply forge the. I mean, you can forge the signature, you can forge the names, but you will not be able to authenticate actual data packet because it will not be rooted in your root of trust.
If there is one single point that is, in a way, the gateway.
I mean, if there is a gateway that is not.
And but it was the case in the scenario. So there was this big gateway, and everything goes through and out from it. So there you have a single point of failure that is like every
unfortunately, if there is a single point of data transfer, there is a single point of failure. But I may be kind of extending that example from single aircraft for like multiple aircraft. So if one taken over aircraft is flying, there is another way of getting some information from outside the network. So as long as there's a multiple ways, like multiple physical connectivities that can get the interest out of this environment, like maybe it's a neighboring Humvees or something on the ground can get that information. So you have to have multiple ways of getting out, and NDN can easily utilize those ways, like without requiring any additional IP addresses. So to build up on kind of this picture, so kind of remember there is a name of the data, name of the key as part of each data packet, and I will get back to the root of trust in a few moments. But if we just look at the names of the data and keys, we can see that some of the data is valid if it's signed to, we can define that for the data to be valid, it has to be signed by the key following the proper naming conventions. So effectively, key can define the context for the data or security context of the data, or vice versa. Data can require specific context of the key. So in this silly example is that a camera from a UCLA campus have to have a key that belongs to UCLA campus and some building attribution versus if it's signed by the TV's keys, then it's a kind of a bogus example. But the one thing that I really want to emphasize by showing that silly picture is power of names. So it's not just the power of names, but rather using names to restrict what the keys, what is the power of keys themselves. And there was a conversation during the break about, what if a key is compromised? But that's actually the point here. If key is only valid to authenticate a very small portion of data, the compromise of that key would be bad, but would only affect a very small portion of kind of subsets of data. And we have to deal with that specific portions. So this is a very simple example, just highlighting that UCLA campus, kind of this AR feed or like video feed has to be signed by the something that with the word cameras, and that's something with UCLA. But you can utilize these names in kind of several different dimensions. Of course, there is some limits of what you can do with just name matching, but you can imagine this can be location-specific things that we can match between names in data and a key, data type, producer type, and you can also add the temporal component there to specify that this key is only valid to kind of produce data at that specific date, or you can actually add a time. And geographical location, this can be actual GPS coordinates, or in that sense is just a building number or building name. And what we have built to utilize this method, and this is just a little bit advertising of technology, is the concept of trust schema. So this is just in kind of some automated way to define the rules, to define the trust model for a specific application. And to give you an example, kind of, you don't really need to read what is happening here. But the idea is that there's some general rules like to defining what this application expects from the application names and what it expects from the key names to exist in there. So this part is defined by the application developers, like and something similar can be defined for the example that Tamer was talking about before. But then there is a lower part, this is an extremely important part, is trust anchor. And it's not just a trust anchor in sense of a set of CAs that sign private, create certificates for some domain names, but it's rather a trust anchor for that specific environment. And this is what we're trying to kind of emphasize with name data networking is we want to utilize the notion of hierarchical names and associated trust anchors for those specific names. So this trust anchor is not just blindly assigning some random names that and others just trust because they trust those trust anchors for everything. But rather this one is specifically for UCLA. For other environments, there would be specific kind of semi-equivalent of a DNSSEC environment where you don't have a trusted root and have some other relationship between kind of some other ways of actually figuring out or pre-configured trust for those local trust anchors. Before, what I mentioned was about the authenticity of the data, but its important component in especially military environments is to secrecy of the data. And for this kind of part, the basic part is kind of you have to encrypt all the data. So in NDN, the problem of secrecy actually moves to the level of key distribution. So you have to distribute the decryption key for the data has been produced and encrypted in order for somebody else to actually get access to this data. And we have a few solutions, and this name-based access control is one of the solutions that we're trying to explore. The picture is a little bit complicated, but what I want to highlight here is for data management, in NDN, you may want to separate the actual data production, data consumption, but also there is a distinct component for data ownership. So there is somebody else, kind of maybe outside the environment, who decides some policy of data access, like what data can be accessed by whom. In NDN, we try to utilize a naming convention for this specific purpose. So data owner define a policy that FIU parking, the whole namespace, can be accessed by Alex. Or like, so you're just defining this small policy namespace that is allowed, and who is allowed to access this namespace. It's acting as a synchronous intermediary between the delivery of actual encryption key for the specific pieces of data to the guys who will be accessing those pieces of information. So if I maybe just to give a different kind of different way of describing this. The actual data is being produced under a specific namespace, is encrypted with a unique symmetric key. That symmetric key is being encrypted by a specific namespace key that the data owner is managing. So there's a data, say FIU parking PG4 level 1 sensor. That key, that symmetric key, is being encrypted by the public key of the FIU parking. So now the FIU parking is kind of the private key for that can decrypt all the individual symmetric keys. And effectively, the job of the data owner is to deliver that encrypted private key to whoever is authorized to decrypt this private key. who's supposed to be authorized.
And what I'm saying, what I understand here, that you confined to use the RSA as that is the only asymmetric algorithm that you can actually use the public key to decrypt.
In this solution, we have explored RSA specifically. What I'm not showing on this picture, and unfortunately I'm like over time right now, is the data owner in this example just defined FIU parking namespace, but it actually could have included the temporal component to define that this key is only valid for a specific time period or specific time periods. So we played with a kind of NDN fit, like our mobile health NDN application, to define, to give access during the daytime, access during different time. You can define access, like play a little bit more with kind of this prefix of data access. There is an alternative, or kind of a new solution that we're trying to explore is have additional kind of move experiment with other encryptions besides RSAs is with attribute-based encryption. It adds additional level of flexibility of what you can do, like what kind of a granularity of access you can provide, and kind of separates data ownership from actual key distribution. So you don't need to distribute as many keys as you would need with the standard process. So with NDN, you can enable very easily the ad hoc multi-interface communication, DTN-style communication, and yet everything keeps secure, because every single piece of data that is being communicated on a wire has signature, is encrypted. And you can utilize the same kind of interest data mechanism to get access, to get the keys to authenticate the data, or to get keys that has been provisioned for you to get access to the data. And kind of everything is built in because of we utilize the names, these hierarchical names that are pretty flexible, and data security that I already mentioned.
I have some concerns about the security here, in the sense that if we look at tactical networks where you have limited capacity on the channels, and you add signatures, asymmetric signatures, the overhead really explodes. So that is one concern.
So I totally agree with that. One of the very first thing that we noticed when we started looking at this was that exact same thing. And so, but you can do other things other than signing every single packet. So one of the things that we explored with, and I think we have a paper on that, was that we do hash chains. For the data, you basically, hash the data and apply the hash of the previous data to the next data, and then you sign just the last one. And that, from a computational resource perspective, much lower, but it gives you the same level of security. Does that make sense?
And then my only concern, if I think this as an alternative to current security systems, it also means that if you add a signature to the application, that means that you have to put the trust in that end. Meaning, for instance, for a military system, that when you have classified information, you have to certify and approve all items, all applications, all computers where your application run, in order to produce something that could be certified or applied for classified information. So just suggest consider that.
Right. That might be like that might show up in my very second slide, just because there is a DARPA program that I'm going to talk about in a few slides that is meant to sort of look at some of these issues, specifically in game context.